Hello everybody. So we have this question about rapid mixing in a conventional water treatment plant. So we have a 15 million gallon per day water treatment plant has a rapid mixing unit with a velocity gradient of 800 seconds to -1 and a detention time of 12 seconds. If the water temperature is 70 degrees Fahrenheit, the dissipated power of mixing horsepower is most nearly, and we have 4 solution options. So before we go ahead and solve this question, let's talk a little bit about the conventional water treatment plant. So in a conventional water treatment plant, we withdraw the water from a water intake like a river or a lake. So this is a river or a lake. And then here we have our water intake structure. And then we go to the screening unit. And in the screening unit, we separate the large pieces of garbage. And then we go to the following process, which is coagulation. And this is where the rapid mixing is happening. And then after coagulation is the flocculation, the slow mixing. And after flocculation, we have our successive processes like the sedimentation and then followed by filtration and then disinfection and then distribution or pumping to the consumer. Some water treatment plants has a softening unit, but this is the major process in a conventional water treatment plants. So the question is talking about rapid mixing, and this is happening in the flocculation process. So we are here. So now let's go back to our question. So to solve this question, we use the mixing equation. And in the mixing equation, we have the velocity gradient, G, equals the square root of the dissipated power, P, divided by the dynamic viscosity of water multiplied by the volume of the mixing tank. So we have our velocity gradient given as 800 seconds to -1, and we have our P is the unknown that we are looking for. We have the dynamic viscosity of water, and this is at 70 degrees Fahrenheit. And from the physical properties of water tables, we can find the dynamic viscosity of water as 2.037 times 10 to the power -5. This is pound second per feet square. Also, we have V, the volume, and we can easily determine this from the detention time multiplied by the capacity or discharge or Q. So let's go ahead and find our volume here. So volume equals the detention time, 12 seconds. And let's go ahead and convert everything to hours. So to convert seconds to hours, we divide by 3,600, and then we multiply by our discharge, which is 15 million gallon per day. And let's go ahead and convert the million gallon per day to gallon per day. And also we converted our seconds here to hours, so also let's convert our day to hours by dividing by 24. And also we have gallon here. To get into the equation, we need to convert the gallon to cubic feet. So we divide by 7.4805. And we simplify this more to get our volume as 279 cubic feet. So now it's just a plug and check equation, and we put our numbers in this equation. So we have our velocity gradient as 800 equal square root of P divided by 2.037 times 10 to minus 5 times our volume 279. And let's simplify this more. 800 square multiplied by 2.037 times 10 to minus 5 times 279 of the square, so we get rid of the square root, and this is our P, which will be equal to 3,637.3, and this is pound-feet per second. This equation gives the power in pound-feet per second. So let's pay attention to the units. Do not go ahead and pick answer D because it's close to this answer. So the question requires the power of mixing in horsepower. So we go ahead and divide this by 550 to get our P as 6.6 horsepower. And this is answer B.